Welcome to the third lesson of Module 3, Digital Solutions for Energy Efficiency in Data Centers. In this lecture, we focus on another powerful digital tool, simulation and digital twins. These technologies help operators test, predict, and optimize data centers operations in a safe and controlled way. A digital twin is essentially a dynamic virtual copy of a physical system. In the context of a data center, this means building a detailed model that represents not only servers and racks, but also cooling equipment, power distribution units, airflow paths, and even the building itself. What makes a digital twin different from a simple simulation is that it is continuously updated with real-time data. Sensors throughout the facilities collect information on temperatures, power draw, humidity, and workloads. This flow of data ensures that the twin mirrors the actual state of the data center at every moment, creating a living model of the facility. The practical advantage is that operators can test changes in a virtual environment before applying them to real equipment. Imagine an operator wants to raise the temperature set point in the server hall by 2 degrees to save energy on cooling. Doing so directly on live systems could risk overheating or unstable performance. With a digital twin, the operator can simulate the change in a risk-free environment, observe how temperatures, airflows, and energy consumption would respond, and then decide whether it's safe to implement in reality. This reduces uncertainty and supports decision-making. Digital twins are also valuable for capacity planning. Data centers are constantly expanding to meet rising demand from cloud services, AI workloads, and streaming and storage. Adding new racks or adopting liquid cooling systems involve large investments and decisions that are difficult to reverse. Through simulations, operators can predict how the facility will behave under different growth scenarios. They can model the impact of adding high-density racks or switching from traditional air conditioning to liquid cooling, or of integrating on-site renewable energy systems. Instead of trial and error, decisions are guided by data and predictive analysis. Another major application lies in resilience testing. Data centers must operate continuously, but failures are inevitable. A chiller may fail during a summer heatwave, or a power outage may affect one wing of the facility. Testing these situations in reality would be too risky, but a digital twin makes it possible to simulate failures, study the impact, and plan corrective action in advance. This approach not only improves energy efficiency, but also strengthens reliability and business continuity by highlighting weak points before they cause disruption. The integration of digital twins with artificial intelligence takes the concept further. By combining real-time data with machine learning, the twin evolves from a passive model into an intelligent assistant. It can predict future states of the facility, identify inefficiency before they appear, and even recommend proactive interventions such as redistributing workloads, adjusting cooling strategies, or resizing power supply systems. In this way, the twin becomes part of the continuous optimization loop, learning from the past patterns and adapting for future conditions. Although still in its early stages, the adoption of digital twins is rapidly growing. Hyperscale operators are already using them extensively to design new facilities and refine the operation of the existing ones. Research projects are experimenting with smaller scale implementations, making this tool increasingly accessible to colocation and enterprise data centers. The more complex and energy-intensive the facility, the more value of a digital twin can deliver by improving both efficiency and resilience. In summary, digital twins and simulation bring foresight to data center management. They allow operators to test scenarios, anticipate problems, and optimize performance without risk. Together with monitoring, predictive maintenance, and AI-driven automation, they form a complete set of digital tools for improving efficiency. This lesson concludes Module 3. Across the 3 lessons, we have seen how digital solutions can transform energy management. In the next and final lesson of this module, we will take a more practical approach. We will work through a hands-on lab using Python to simulate energy monitoring and optimization in the data center. This exercise will give you the chance to see how the concepts we have discussed, metrics like PUE, anomaly detection, and what-if scenarios, can be applied in practice with real data and simple code.